Good. Welcome again. And thanks that you are here, especially because also of this nice weather. I hope also because of the lecture. And I hope I can leave you for tonight to enjoy at least the evening. But we have kind of an extensive program ahead of us today. So we will continue on feature extraction and matching. So the last time we spoke about corners and key points. It's already 3 weeks ago. We spoke about corners and key points. We spoke about how we can describe points, meaningful points in the image, and how we can do the matching. Today, we're going to look on the edges. You remember the last time we've selected the key points because they mark kind of an extensive or of a good feature representation in the image to describe certain parts in the image. And we also said, well, it could be also that lines and edges are kind of meaningful, and especially on those type of features we will also look today, and we will especially talk about edge detection and what we can do with those detected edges. We speak about half transformation, we speak about template matching, all of those algorithms, this classical computer vision algorithms kind of also today extensively used parallel to deep learning techniques we will discuss or start discussing today. And then in the next lecture part, we will focus on segmentation, where we also reuse a lot of those concepts which we learned here in the feature extraction chapter to basically find homogeneous parts in the image to separate between background and foreground structures, and also, for example, for specific object parts. So next time we have two guests. I will be not here, but it will be another offline session, so it will also take place here. And two of my former PhD students, Larissa and Sebastian, will take over. Sebastian is one of my PhD students, and Larissa was also or is also a PhD student in another field. She works with LiDAR techniques and especially takes care about 3D reconstruction from an automotive perspective. Both work at Daimler, so they bring a lot of experience, especially in terms of classification and convolutional neural networks with them. So I'm happy that they agreed to do this lecture, and I think they bring also extensive knowledge with them. Are there any questions regarding the last lecture parts? Yeah. Today's slides? Yeah, I will do it afterwards then. Actually, I changed today something there, so it didn't make sense to upload them before. So, okay, more questions? And also those topics will be part of those Q&A questions that I will hand over roughly around mid of July, so that you have enough time to prepare for the last session where we also discuss. And I will also show you some other questions which will prepare you for the exam a bit better then. The last time the exam was roughly mid of September, quite late. Actually, I don't know if it's already online or if it's planned already. Do we have a date already? Also mid of September? Great, okay. That's good. So it's already in campus. There's a specific date already. Okay, I don't know about that. I have to watch it up. Good. Then 21st of September. Okay, that should work. Okay, and with those questions at hand, I think you are quite good prepared then. Okay. Then let me see if I'm still audible here. Works. Recording is taking place again, right? So if you have something against it, then you have to speak up now. Otherwise, your voice, if you say something, will be recorded. But it's only for you, so to prepare at home a bit better. Okay, Then feature extraction matching, part 2, edges and lines. So today, as I said, we will especially talk about edge detection in image. We will see how we can basically produce such detected edge images like that here and what we can do with that, especially when we talk about Huff transformation. That's a very great algorithm where we switch between parameter space and image space to find actually objects, to find actually parametric object structures based on those extracted lines. And with Huff transformation, you could do also something like that, right? So based on the extracted contrast differences, which show you basically the road markings, you can have a parametric representation of the road lane. So this was also extensively used before deep learning. And in some ADAS system, it's still kind of a Huff transformation running there, which does your lane recognition, or it's just road markings recognition for you. We will also then look about template matching techniques. So there we also see how the chamfer matching works. Also the chamfer matching has as a base kind of those detected edges and tries to fit some shapes in it based on a distance transformation. And with those techniques, for example, you could detect pedestrians or other more complicated objects. Also traffic signs have been detected with distance transformation, and we will see how that works later then. Okay, let's go. So let's start with looking on this elephant image. Is it clearly seeable for you, or should I make it a bit darker here? Is it okay for you? Yeah. So you see two elephants here. So if I give you now the tasks to extract the boundaries of those objects here, so what would you say? Where are the boundaries in the image? So how would you describe the parts of the image which you would decide this is a boundary and this is not a boundary? Where the intensity changes. Very good. So where is that the case? Here, maybe, yeah. Also here, the legs, here, for sure. Where will you have problems? Okay, and is that the boundary that you want to have, or would you say this is a boundary which I'm not interested in? Why? Because then I can see both elephants. Otherwise, I would be. Yeah. The answer was quite correct. So especially in those parts of the image where you have a clear contrast difference, intensity change, you are able to extract the boundaries or the edges, in this case here, between the sky and the elephant here quite well. But other boundaries, especially between objects where the contrast differences is quite minor, then you have a problem extracting the correct edges here. And this is especially the problem in this task. So if you ask a human to draw the boundaries, then the human would exactly respond as you did, right? He would draw the boundaries like that. He would clearly separate the two elephants of each other. He would separate the two elephants from the background and so on. And here you see multiple boundaries drawn by humans. So everyone answers basically the same. Everyone separates clearly the boundaries also between the objects. If you ask a machine learning algorithm to do that or a computer vision algorithm to do that, then it rather looks like that. And especially the boundary here where you have no contrast differences will be missing, right? And this is one of the main problems in edge detection. You would like to have those things, but you cannot have that solely based on contrast differences. You have to do something more intelligently or work with different regions where you can also cope with different contrast differences and also be able to draw some lines here. It improves a bit if you find other techniques to do that, but especially the borders between the two elephants where you have just a gray color and no intensity change is quite hard to do that automatically. What would you say here? What is the boundary in this image? Say again? Actually, that's exactly the right question. What is meant here? What is the boundary? What object is of interest, right? So if I show that an algorithm, he doesn't know about what I'm interested in, right? He does not know about that this thing is some kind of object that I might be interested in. So if you would ask a human to draw the boundary on this image without giving him more information, then he would just ignore that part inside this bowl, and he would just draw kind of the outer shape of this clothing here and ignore basically, what is it? It's kind of a coffee or whatever. You would just ignore those parts inside here. If you ask a machine learning algorithm or computer vision algorithm, you would actually do a mix between both, right? You will not be able, because of missing contrast differences, to draw a clear boundary here, because here kind of the contrast differences between this shape is quite minor, but he is kind of extracting the contrast differences here in the middle, and without knowing basically if these are objects of interest or not. What would you do here? It's kind of a sea anemone. Not sure if I spelled it correctly. Sea anemonia. What would you say? What is the boundary here? Yeah. Yeah. So this is quite a complex object which also have kind of some parts here around, right? It's not only this part, right? So the object, the sea anemone, is kind of also extending to here, and this is also hard for a human to have a clear understanding what is the object and what should be drawn here as a boundary or not. As you said, might be circuits here, but I expect also different answers from different humans, which would just draw a boundary like that around this here. And this is kind of hard also for the human to do that. So let's talk about an edge detector which is, or which was and is quite famous still, which is one of the most used kind of pre-processing algorithms in computer vision still. It's the Kenny edge detector. And the motivation for that is that you want to basically reduce the amount of data and filters out useless information, right? Those are the edges, right? If you can extract the edges, then you have the major part of the information which could potentially describe objects or other important part of the image quite well. You preserve the most important structural properties normally, right? You could also lose something, but if you do it right and if your object is at least clearly separable from background, then you could preserve the structural properties. And this edge-based detections, those are also the basis for the segmentation. So, for example, for segmentation between foreground and background objects, so between object of interests, foreground objects, and background things which are not of interest for you. So we will speak later about that. But this is a motivation. We will do kind of with the result of this edge detection algorithms, we will use that as a pre-processing step and do some more fancier stuff afterwards. So what is an optimal edge detector? So an optimal edge detector will do some good detections for you. So you would like to have some low number of false positive edges, so where there is basically nothing. So you would basically try to avoid that the edge detector is kind of focusing too much on some noise in the intensity level. You would also like to have a small number of false negatives, right? So if you miss some important part, you cannot recover the structure of the object afterwards. So you would like to have that it has a good localization, right? So this one would be a poor localization, where this one would be the most correct localization, right? And if your edge detector does something like that, well, apparently here is a part missing, right? This would be a false negative, and here are too many false positives, so just too many responses for this single line. So in the ideal case, you would also like to receive a single response like that, and not too much false positives, too many responses for that. So those are the three criteria for an optimal edge detector, and this canny edge detector is trying to actually achieve that. And a canny edge detector makes an important assumption. It says, well, the step edges are corrupted by just additive Gaussian noise. So, and now from some of the last lectures, you should know kind of a filter which gives you kind of a smoothed extraction of high frequent part of the images. Do you know that filter name again? Well, the Gaussian filter is a low pass filter, but what are edges again? Sobel filter, perfect. So a Gaussian filter would be the low pass variant, and now the Sobel filter is basically the derivative of the Gaussian filter. So remember, the filter matrix is 1 to 1, right? 0, 0, minus 1, minus 2, minus 1. Basically, it's a combination of a high pass filter and a Gaussian low pass filter. So it gives you a smoothed version of the high frequent part of the image. And that's exactly also the reason why we use it, because this is the assumption here that we make here, right? By using the Sobel filter, we say, well, the noise might be an additive Gaussian noise, and indeed the canny edge detector uses this first derivative of the Gaussian filter, which closely approximates this assumption. And the canny edge detection filter is basically implemented in all of your computer vision toolboxes nowadays, and you can easily call it in MATLAB, for example, by just executing an image, a gray value image, and taking the edge function and use kind of the canny as a keyword, and you get the canny edge response here. So the canny edge detector is basically coming with 4 important steps. So the first step is you filter your image with the x and y derivatives of the Gaussian, so the Sobel filters in horizontal and vertical directions. Then you find the magnitude and the orientation of the gradient. So what's the magnitude again of an edge? Yeah. So again, in formulas, what is it? Yeah, Euclidean length, basically the square root of the power of 2 of both components, basically. And then you have the magnitude and the orientation. You could calculate it with the arctangents function by just using the horizontal and the vertical derivative to get also the orientation of the edge here. Then you do a so-called non-maximum suppression. So this is the important step to get rid of kind of too much false positives beside the actual edge. So you take only the maximum in a local window, and this thins out basically. And remember, this is one of our criteria that we would like to have. We want to have a single response, so we want to have a small line, a thin line, and this step, non-maximum suppression, gets that for you. And then at the end, we connect basically a single part of the edges with each other. This is called thresholding and linking. There we use hysteresis. Hysteresis is basically, you might know that from other applications, hysteresis is always using 2 thresholds, a low and a high threshold. And something which is above the high threshold is always accepted, and something which is between low and high is only accepted when it's quite close, or timely wise in other domains quite close to some high response, and everything which is below the low threshold is always rejected, right? So this is kind of a method for linking and thresholding it. We will later see how that works. And that brings you basically corrupted edges together and makes them connected. Okay, so we have discussed that the derivative of the Gaussian filter is basically the Sobel filter that we apply here. That looks like that. We have it in the horizontal and in the vertical response. So we have in this part we have the vertical edges filtered out. In this part we have more the horizontal edges filtered out, and then based on the arctangent function, we can also compute the orientation at each place using those two components. And we are not interested in too much accuracy here of the orientation. That's why we just use a binning of the orientation in 4 discrete angles. So 0, 45, 90, and 135 degrees. So we skip the sign, right? We only are interested in those 4 orientations, and everything which is, for example, between 0 and 22.5 is going to 0, and everything above 22.5 and between 22.5 and 67.5 is going in 45 degree, and so on. And then we can calculate the gradient magnitude. That's the image that you see here. And we can also visualize our orientations. That's the image that you see here, basically. So those were basically the first 2 steps, right? We have now the orientation and the magnitude. And now we use this non-maxima suppression to thin basically our edges out. So we use the orientation at each place for that. So we basically compare the edge strength of the current pixel to the edge strength of the pixel in positive and the negative gradient orientation side. So we look basically left and right in this part here of the image. Or if you would have a horizontal edge, we would compare top and down pixels with each other. And we select this place or this edge pixel only if it's a clear maximum, and otherwise we throw it away. Basically, this is classical non-maxima suppression, and it basically leads to a thinning out of these edges. As you can see it here we have quite a bold response. We are actually not interested in that because that brings just some not clearly. You cannot really locate the edges correctly like that. So you would rather like to have a single response at each edge like that, and this makes your non-maxima suppression. And then based on the non-maxima suppressed edges, we do the thresholding and linking. So we use this double thresholding here with the low and the high threshold, and everything what is above the high threshold we accept immediately, and everything what is below the low threshold we reject immediately. And now we do something to make sure that we also accept here between the low and the high threshold. We would like to figure out what should we accept and what not. And we do it just with a so-called plop analysis, or at least this is the implementation for it. Basically, you're just interested to accept everything which is between the low and the high threshold, which has a pixel or an edge in the neighborhood which has one high threshold or above, right? So at any pixel in the image that has a value greater than th, it is presumed that, I don't have to read it, I can just explain it. So basically here you normally implement it with this plop analysis. There you check everything which is between the low and the high threshold. So this would be that one. So this is a kind of a weak edge detected position here. And now you look in the neighborhood and check, is there a strong edge in the neighborhood? And if yes, then this one is accepted as an edge. And if not, as it is in this case, this one is not accepted as an edge. Yeah.
And if we accept the pixel, we also treat it like a strong pixel, right?
Yeah, at the end, you don't make a difference anymore between strong and weak, right? This is only a helper function basically to get some continuous good edges. At the end, you receive a binary image, so either 0 and 1, right? And 1 are your edges, and 0 is everything which is not an edge, basically. And indeed, you will accept that as a one, right, as an edge, only if there is a strong edge pixel in the neighborhood of that. So this neighborhood could be arbitrary sized big, right? Here you have just an 8 neighborhood plop analysis. You could also decide to make it a bit bigger. So with that, you would be able to kind of connect far apart segments even better. But normally an 8 connected neighborhood is used here. Yeah.
This is not done intuitively, right? So only scan picture one, then you get some extra edges, but you don't do it another time.
No, you do it only once. Yeah. So this could be also done in parallel, right? So you just try to close some holes between the strong pixels here. Here you see the result basically. So you have once visualized the high threshold, the strong edges, and once visualized the low thresholds, the weak edges. So you see quite a lot, and this is also kind of some noise in there which you don't want to have. And now you do this thresholding and linking, and you see, for example, here in this shadow part where you have some weak edges available, those are kind of removed because there's no strong edge in the neighborhood found in this parts, and also on the wall here, like here in this part, some of those noisy weak edges are removed by the thresholding and linking, and especially those lines where you want to have an edge are also then connected then by this step. So another result here, and you see here especially there are a lot of details, right? The feathers of the head here. The question is now, do you want to have that or not? Could you imagine a method to get rid of those noisy parts, to focus on the stronger edges? So what could you do here? No, you would like to, for example, only allow kind of edges which have a really big contrast difference in the original image. So, for example, I would like to only allow the head boundaries here like that because they have a quite of a high contrastive difference. So, what could you do here? Increase the lower threshold. Yeah, that's a good point. So, what else could you do? What are we again using in the first step? Sobel filter, and what parameter is important there? So what are the two filters which are combined in the Sobel filters again? So say again. You have both of that. Yeah, you have the horizontal and the vertical Sobel filter, but what Gaussian filter, and what parameter does a Gaussian filter have? What parameter do you have in a Gaussian filter? The variance or the sigma, right? And now if you want to just focus on basically the major edges, right? So, but the term major edges is not really correct. You would just focus on the edges which have a high contrast difference in the image. So you would be able to reach that also with increasing the sigma. So smoothing the image basically before you apply the canny edge detection, or just use a bigger sigma in the Sobel filter, and this would result basically in removing basically those lower contrast parts in the image, where you in the canny edge detection then you will not find the edges here in that part again. So this is one result of that. It's a movie scene from stormy weather, and the canny edge detection algorithm runs much faster than real time here, right? So normally in a movie you have 30 frames per second, and the canny edge detection nowadays can be run nearly in 200 to 300 frames per second, even more. Especially when you implement it on GPU, it's really fast, and this can be executed and calculated quite nicely. And you see that the most important part of the images are still there, right? You could still recognize these two persons, you could still recognize the orchestra here, and you could still recognize the instruments which they are playing. You could recognize what those guys are doing, right? They're dancing and how the feet are moving. So that basically shows that the most important information is preserved in a really compressed fashion, right? So you are only keeping a binary image like that, 0 and 1, and only keeping the edges and the localization of the edges. Any questions to that? Yeah.
So now that a lot of the shadow were not which is something that you normally not do, which you ask to draw it out. Is there a problem for forest edges from shadows?
I mean, per definition, as we did it now, right? We declared edges just as a contrast difference, right? And for that, it's just the same as a difference between object parts. It would be also a difference between shadow and not shadow. And indeed, shadow removal is an important part in computer vision, right? There are really sophisticated algorithms also with deep learning, which try to remove shadows from the image. So this is not really easy, because how do you know if it's a shadow or not, right? So it could be also a dark object somewhere lying on the floor, and this is or some objects in the background which has a low contrast difference. So that's quite an important and also complicated problem. And there's a whole kind of domain in computer vision which takes care about that. More questions to that? So you figured out that there's nice music in the background of this movie. That was quite irritating, because I had the music and I have to speak over the music. Okay, then half transformation. Who of you have heard of half transformation already? Okay, okay. Two of you. So maybe can you explain it roughly what the half transformation is? Okay. Mm-hmm. Okay, and what are our features? Hmm? Those are the parameters of the line, what you just said, I think. So what are the features? So what is the basis for the half transformation? So what features do we need to extract from the image to perform the half transformation? The edges, what we just discussed, right? So the edges are our features, our base for the half transformation. And with the detected edges, as we could do it with the canny edge detection, as we just learned, we could now basically find a parametric way of shape fitting, and we will now look on how to do that. So let's discuss it first with lines. And indeed, you said it correctly. There are two spaces basically, right? There's the image space, and a line in the image space, you all know, is described with the parameter m and b, and our variables in the image space, which is the image location, is y and x. So setting the parameter m and b will give us a line here in the image space. But there's also the parameter space, and the parameter space switches the roles of parameters and variables, just simply. And this is a kind of a dual problem. So by switching the role of those parameters and variables, we end up in the parameter space. And now our parameters are the former image locations, y and x, and our variables are m and b. So you would ask now what helps us that. So let's have a look on an example here. So in an image space, if we have a line like that defined by our parameters m and b, if we switch now to the parameter space, what is the form or the corresponding shape or points in the parameter space? What do you think? Why is it a point? Yeah, perfect answer. So a line in the image space becomes a point in the parameter space. Just the parameters m and b describes this line in the image space. That's quite easy. Okay. What would be a point in the image space become in the parameter space? And what is the meaning of this line in the parameter space? So you have now a line in the parameter space, I agree with you. What does it mean in the image space then? Exactly. This line in the parameter space describes all the lines passing this point in the image space, right? And this is interesting now. And this is the base foundation of the half transformation, right? And we will see in a few minutes why. So if you have 2 points, what will it become in the parameter space then? Okay, and will they meet each other or not? Exactly. So this point here, where the 2 line meets here, this is exactly the line spanned by those 2 points here, right? Now remember the feature that I just mentioned, our edges are the base of this everything. So just think about those points not as points in the image space, think about those points as features, as our detected edges now, right? And imagine now that you have corrupted edges, right? You have only 2 points given, right? You don't know if they belong together, if they are lying on the same line. And now you just use this parameter space transformation and see, well, from those 2 points, we get 2 lines which are meeting each other in that point. And exactly this crossing here, this intersection of the 2 lines, describes quite a correct line through those 2 feature points in the image space. If you add a third line now, well, this is also kind of lying on the same line. That's also then a line which is crossing here in that point. If you add this point, what will happen then? Will it go also through that point here? No, no, exactly right. That will. So from this basically point, we can also span a line through all the other points, right? But it will not lie on the exactly same one, right? And well, this is kind of the foundation. So now 2 questions. What is now with noise? So we just discussed the edge detection is not really ideal in terms of we will also have kind of noisy measurements in there. What will happen then? They will not meet exactly in this particular point. So what could we do here? Allow a region, yeah? So what is, if we define those regions in the same size everywhere? So what is the term for that? Yeah, so if we know the noise, then we could define this region. But if we have now a region everywhere in the same size, So we call also that binning or quantization, basically, right? So we take a binning in a parameter space. So we say everything which falls inside a specific region is kind of this point, and everything which falls inside another region is then this point, right? This is binning or quantization. And this is the foundation of our famous half transformation. So what we first do here is we quantize this parameter space, right? This is our binning. So we cope with noise by that, right? And we create an accumulator array. So an accumulator array takes this parameter space, this quantized parameter space, and counts basically how much votes you have at this particular region, right? So having these two lines crossing here from two feature points in the image space, we have two votes where the two lines intersecting, and only one vote basically where there's only one line, right? And extending it to three lines, then we would have a free vote here, right? Three lines crossing in this intersection here, and so on. And this is all, right? This is the complete algorithm already, right? And you find here the pseudocode for that. So at the beginning, we have this accumulator array initialized to 0 everywhere. And then for each image feature edge, basically, X and Y, we will check where does it end up here? Where does the parameter, so in terms of the line, where does the parameter, where do we need to increase the vote here? And we increase the vote exactly on this parameter space level where we have basically the lines entered here. And then at the very end, if we have done it with all our feature points, with all our image edges, we just find the local maximum, which is here, and we have extracted our main line described by our features in the image. Any questions so far? Is that clear? Will get a bit more complicated now, so it's important that you got the main idea. Okay. How big does the accumulator need for representing arbitrary lines with this formulation that we had just so far? Remember, we have M and B as parameters, so we have the standard line formulation. So how big do we need to have M and B? Why?
For example, if I have then I have infinite
Slope. Yeah. Perfect answer. And is it a problem or not? Yeah. So the answer was, I repeated for the online candidates, the answer was well, M and B could be infinity. So why could B be infinity? What?
I don't know if I multiply it also across
the y-axis. No, it will not cross the y-axis, right? So B will also infinity. And every time when you have something which can go to infinity, you have a problem. Especially in computer vision, you have always a problem because you cannot calculate with infinite values. And having kind of a line representation which would only work if you can work with infinite values, and you cannot represent basically a vertical line with that. That's just dumb, right? You you need to do that because there are vertical lines in the image. There are vertical structures like houses and buildings. They have vertical structures, so you need to find a way to cope with that. So we have infinite slope M, and this makes the parameter space of M huge and the parameter space of B also huge because M can go to infinity. Do we have a solution for that? Okay. good solution that should work. But then you have to touch the image multiple times, right? Which is might be not so efficient. But very good answer. So you could rotate the image and apply the half transformation multiple times. That's a good solution. What else could you do? Are there other representations of lines that you could imagine? Ooh. Okay. Come with a lot of great solutions. I have not thought about that. Very good. Think about if that works. Well, I mean, yeah, and indeed you are interested in a parametric representation, right? So the Fourier transformation, and you have to do it in Fourier space. Yeah, you have they're not, and you have a periodic repeating signal, so you don't have this line perfectly normally, right? You will have a lot of noise also in there. I will think about it. What else do you have in mind? So are there other representations of lines, other parametric representation of lines you know about? Yeah. And talking about angles, you're quite close already. So what, thinking about trigonometric functions, there's something called the Hesse-Normal form, right? So this is another line representation. I know it's quite far away already. It was probably in the gymnasium somewhere, but this is using the Hesse-Normal form will cope with that problem. Because you could also, at least you could basically represent all types of lines with that, right? And you have also the two parameters, the theta, the angle, and the radius r basically, which gives you then a line representation. And you span this half space now by saying, okay, well, the theta angle I can just fully represent between 0 and 2p basically, right? This is my full angle I can represent here. But for r, I have to find an r max, right? So the distance from the origin, I have to define that. And I also have to define then the quantization, right? So this is a trade-off, right? The bigger my r is, yeah, well, the rougher my quantization at the end needs to be, right? So I have to check, I have to take care about this parameter that my search space is not infinitely huge at the end. Yeah. Exactly. I would have said that later, but in general, the half transformation is kind of applicable to a lot of problems outside also the image domain, right? And indeed, if you work in the image domain and if you're only interested in lines which kind of are in the image, then you can nicely set your R max. Well, so if you have this representation in a parameter space now, so what would a point become in parameter space now? It's getting even hotter in here, right? Is it? Shall we open the windows again, maybe? The door? So what would a point become here in a parameter space? Circle. Other opinions? wave. Good. Yeah, so we have sinus and sine and cosine, right? And you define basically a wave here. So all basically those points here on this wave are basically defining lines which go through that single point. And yeah, so here it's visualized again. So basically you have those two parameters r and theta, and varying this on this line gives you all the lines which are, even the vertical ones, which are basically on this point, or lines crossing this point. What is here now? So why am I ending here at P, and why is it getting negative? Repeating. So what is that point here? So what do we have here at P? We have here at P, we have -1. Yeah. So the sine of theta is equal to sine of theta plus P, right? So this is exactly the same as this one here. So I only have to represent half of my original 2P parameter space, namely only 0 to P basically. The rest is then repeating, because we are not interested in the orientation of the line, right? If we would be interested in the orientation of the line, does it go upward or downward? Basically, we would like to have that as well, but we are not interested in that. We don't know. Yeah, in this application, it does not make sense. But
if I look at, for example, the edge of the doorway, right? There's no
no, not with single edges, but you could imagine different features, more sophisticated features than edges, which gives you also an orientation per edge, right? So there are also ways to do that, right? You could say some sophisticated techniques. You could say, well, this part of the building or this part of the building is more upside than downside, right? And then you have suddenly an orientation in there.
Yeah.
But in just talking about the simple features that we had so far, just the edges, we are not able to say that. So we will just repeat here again, and our parameter space goes from 0 to P. Then we have multiple points, then we have multiple waves, right? All of those which are defining one line, crossing again in this intersection here. Quite the same as before, only that we have waves instead of lines now. And the algorithm is exactly the same, right? Except that we here use now basically to find our accumulator vote, or to define our accumulator vote, we use this parametric function. The rest basically is then the same. So we find the local maximum in the accumulator array, and we use then this parameter of the local maximum to define this line then in the image space. So an example, so if we would have those edges detected in the image, right? So this would be our votes based on these waves here. So you would clearly see here a maximum here, which you can easily pick to define this particular line here. Also in this example, so you might be interested to extract this kind of fence here. And you see here that you have multiple of those votes, right? Each of those local maximums are corresponding basically to the extracted edges of this fence here, the vertical ones and the horizontal ones. And by that, you could also define or identify more than one local maximum, right? If you're interested in that, and clearly detecting basically the fence in the image, because it has just a simple line structure. What happens now if we have noise here? So we said already, we talked before, right? The local maximum is getting more distributed. And what is the countermeasure to do here again? What could we do? We increase the quantization, so we make the regions in the accumulator array bigger. might be not always a good idea, because we would like to have also this accuracy, right, of the line. So at some point, if it gets even worse, right, we will have no chance anymore to identify this line here, right? We will not, even if we increase the quantization, we will not find a good maximum here anymore. So the noise is a problem, and there you can also draw some statistics or to do some experiments based on your application in there. So the more your noise level increases, right, the less votes you get in the correct one, for sure. So you have the same amount of points, but the points are more distributed in the space, in the image space. So they will not end up in the cell or in the right accumulator cell. So the chance will get quite low at a particular noise level. And if you now increase the number of votes, for example, if you would make the sigma parameter in the Sobel operator smaller, right? So you will get more votes, you will get more features, more edges, but also more noise. So you will fill up basically the number of votes in all basically accumulator cells, and for that then you need also to increase the threshold level to make sure that you're selecting the highest vote or the right vote then at the end. So those are the two problems. So the one problem that you have more noise in there, and even if you say, well, I have less points in the cells, right? I need to have more points in the cell. If you increase then the number of edges, then also then by increasing noise level, then you just fill up the accumulators even more, which will not get you around of this problem that you cannot identify the local maximum clearly at the end. So another example here, right? It also works some amount of occlusion, right? As you can see it here. So here you try to identify basically the structure of this device here. And you see here, it's quite working well, but it has also kind of then some problems here where you have this occlusion and you could not clearly identify basically the top and the right border of this device anymore. It's an example that we've just seen before. So this is exactly applying what we learned so far. So now there's a little bit more pre-processing as we did it so far. So a simple canny edge detection might not help in this case. So you would like to have some prior information in there. Where is the road roughly, right? And you would also like to maybe separate out moving objects like other cars. But then detecting basically the line, the structure of the road markings, right? That will give you the edges, the feature points. And with those edges, with those feature points, you could then basically find a parametric representation of this line here. As you see it here, this representation is not ideal, right? In the ideal case, you would like to have to follow the road here. So could you imagine a parametric form which makes that better? Splines, B-splines, and so on, quadratic splines, right? That comes with more parameters, right? So the space where you need to identify your local maximum at the end is bigger, and your search space is getting bigger. So this is one major problem of the Huff transformation. It only works with a low number of dimensions, right? If the number of dimensions gets too high, the number of parameter dimensions gets too high, then the space is too much, because you have to iterate over all dimensions in this for loop, remember? So we had only 2 for loops for theta and r. So if you increase the parameter dimension, then you also increase the complexity, and at some point it stops working. But it easily works if you have up to 5, 6 parameters with CUDA implementations. It even, and if you restrict basically the search space intelligently, then it also works with bigger dimensions in CUDA. And other shapes. So we could also have circles, right? So circle form is represented here like that. So here we have then our three parameters, A, B, and R. And in the parameter space, you switch again parameters and variables. And now same question again. So what does a point in parameter space become? A circle. Yeah? So this points here on the circle are all circles which passing that point, all circles with the parameters passing that point here. Another point here, another point, and you now immediately see this point. This intersection of all the circles in parameter space is what in image space? The middle point of the circle going through all other points. Yeah, I don't have the solution here, but in this particular form, right, and I think you're one step ahead, I'll quickly show you later. In this particular form, you have this intersection of these circles here representing exactly the circle which contains all the 4 points here. Yeah. Exactly. The R is fixed in this representation, so we have only A and B. I forgot to say that. You see it here, so otherwise it would be three-dimensional, right? So you would have another dimension here. But you can also iterate over R then. So then you have 3 for loops. If you would like to have more radius, multiple radius of the circle, then you would have a third dimension where you have to iterate over, and you define your accumulate array over 3-dimensional space. Well, so that what you meant, I think, is, or it goes in the direction what you meant. You could now also apply another information here, namely the edge direction that we have, right? So we have it by the arctangents of the vertical and the horizontal Sobel response. So we have also the orientation of the edge, basically, and we could then define basically at each particular point, if the orientation is known, then this particular point defines basically the orientation to the inside, to the midpoint of the circle. And then this makes our problem a bit simpler because we then have our feature space, our feature point, which is now a three-dimensional representation, namely the location plus the gradient. This one defines just a point in the parameter space because it's clearly defining only this one particular circle, right? And the same point is represented also by parts on this circle, right? So basically, if we would have no noise at all, we could represent one particular circle parameter by just one feature point. Yeah.
Which is now my mistake. So variables A and B still correspond to the middle point of the circle left, the x, y, right?
Yeah, this is not a middle point. Yeah. Yeah. But the only difference is now that you apply another information here, and I think you meant it correctly before. I just was a bit confused with this midpoint. Sorry for that. Well, so the only difference is here that you apply the gradient information, and you could restrict basically your parameter space representation on this particular point here. And this finds a lot of applications. So circles, as you know, are kind of also by humans and also in street scenes. Can you remember about, or can you think about classical representation in street scenes which has some circles? Yeah, so they are not always circles, but a lot of them are circular, right? And half transformation has been used for traffic sign detection. And you could also imagine that you have not a circle parametric representation, you could also have a triangle parametric representation, and that makes it quite nicely applicable for example, street sign detection. Here you have another application. Here you have this shoe here where you try to do some quality checks, right? You try to find out if this the bottom of the shoe is manufactured correctly, and you want to know if the circles here, for example, are correctly drawn, and this could be also then implement an automatic quality check with the half transformation. So here you see basically here we loop not only so we have for each edge point, which is now x, y, and theta, right? We have now different r's, different radiuses. What is the multiple of radius? Radii? Yeah, yeah. So we loop over multiple radii, and for all thetas, basically, we have another for loop here. But we can have this restriction based on the theta that we have given in our feature points here. And then we do the same here. We find the maximum in this accumulator array to identify these nice circles here. We also find coins of different sizes, right? Here you have basically our edge response from the canny edge detection. And now we try to find the copper coins, so with the smaller radius. So here you find then clear peaks basically for this copper coin here with the smaller radius in that part. And you see that the peaks here are not quite well defined, but for a bigger radius here, we have the silver coin, which is the bigger radius defined here quite nicely. We see the local maximum, and we can identify them as well then. Yeah.
Edges in there, which must be set by some arcs or something.
So for about if half transformation is used for fingerprint. Yeah. Yeah, so the fingerprint identification is done by extracting contours, right? So that's basically the same part. So you every time your fingerprint is scanned, then the contours of your fingers are extracted, and then normally they are matched directly, right? So this would be the most basic form, right? You try basically you have a database of all those contour-based fingerprints, and you find just the maximum overlap in this database based on the contours directly. So the half transformation it might work to have a more parametric representation of the, but I'm not sure about that.
I think about where there's like 5 different pictures, and then you have like a huge database for crimes or something.
Yeah.
I think it's much faster, like a more sparse representation.
There are parametric representation, but they are rather work like what we discussed in the SIFT chapter, right? Describing basically local local regions in this fingerprint, right? So you have a high resolution of this fingerprint, and then you define basically a structure in a descriptor, right? And you're searching for that efficiently. But the half transformation might be difficult to apply a parametric form for that. But I'm not sure. I looked it up. Maybe it's quite interesting to comment. Okay, more questions to that? Well, so last but not least, there is also a more generalized representation of that. Basically, the half transformation can be can be applied for any non-parametric shape as well, right? So where you clearly at least can identify basically the outer part of the shape, and that basically makes it not really applicable for the fingerprint type, but for arbitrary objects which can be separated by the canny edge detection basically from the background. So what you need here is basically, let's say this is our template, our object shape that we want to represent somehow. And then instead of saying, well, I have a parametric form for that, I basically sample the points here and store them in a database for later comparison, for later matching, basically. And this database is called the R table here. And the R table stores now basically this angle here, where we have at each particular template point and the radius to a customly defined midpoint, which is normally lying in the shape or in the template, but it could also lie outside the template. It does not matter. So it's storing basically those two values for each particular binarized edge gradient that we have extracted here, right? So taking this as a contour and taking this as some edges that we have defined, we can extract basically our location of this edge, right? And we can also extract our gradient on this edge. And then we draw a line from this particular location of the edge point to our midpoint in the template. We store that angle here, we store that angle alpha here, which is defined by this line spanned to the midpoint. And we store the radius r here for our particular gradient that we have at this location. And this gradient is this gradient is binned. So again, quantized. Let's say that we have 12 values or something like that. 12 values for our orientation. So we bin our gradients to this 12 values, and then we say, well, if we have here a zero gradient, then we store this R and alpha tuple in this row of this R table. And if we have a 45-degree gradient, then we store it in the second row of this R table. And we do that for all the template points of this particular template. So this is the organization of how we represent a template that we want to later find in the image again. And now we have created this R table with our binned gradients here. And the algorithm for matching is then just we basically let's focus on one particular size of the object. So let's first focus on that the template has exactly the same size as we have defined it here in the template. So we would like to find the same size of this template in our image again. And then I get my features again in the images, my feature edges, which are X, Y, and theta, right? And now I'm using the gradient angle theta to retrieve from the R table basically the R and alpha tuples that I have stored before from the template. And for each R and alpha tuple, I compute the candidate reference point by using again basically this formula here. So I have my location, X and Y, I have my radius, I have my cosine and sine of this alpha that I've stored here. And for that, I get my location in the accumulator array, A and B, which is my candidate reference point here. And I increase the count as the voting in my accumulator array at A and B for that. And I do that for each feature point that I have in the image. So for each edge point, I applied it like that. I retrieve always the number of the based on the gradient. I retrieve the tuples in the particular row here, and I increase then A and B in the accumulator, the location AB in the accumulator array corresponding to this candidate reference point here. And I could also extend that by a scale factor, right? and also by a rotation factor, right? Then instead of having a two-dimensional accumulator array, I would have a four-dimensional accumulator array, but I would also cope with different scales and different orientations of this template. And this particular generalized half transformation makes it well interesting also for more complex objects, especially also the number basically of dimensions that I have now for arbitrary sized and oriented objects basically is just four-dimensional, right? And that's the reason why if you know the shape of a rigid object, so of a not changing shape object basically, then the half transformation would be a good choice, at least as a baseline, to say how far can I get with a simple algorithm like that to detect a shape in my image. It's generally quite good with occlusions, and you can also detect multiple instances with the half transformation. It's robust to noise, right? At least to some extent. It depends on the parameters and also the size of the accumulator array that you define. This is bad computational complexity, so if the dimensions increases, then it's not applicable anymore. And it's also not easy to set the parameters correctly because you don't know the noise level, or you cannot really define the noise level quite well. So the exact bin size is a bit tricky to set normally, but it's still quite good algorithm to detect templates. Questions to that? Understandable? Everything so far? I have now 15 minutes left. Let's do it. Okay. Then we have a 10 minutes break. Let's talk about template matching now. So far we have tried to find a parametric representation of our template, right, to identify it in the image, and now we are interested more in the intensity features to do a template matching. And basically, given a problem now like that, so you all might know this children book, Where is Waldo, where you have to find basically this guy in those images here, right? Which is quite challenging. Also for an adult, it's quite challenging sometimes, but kids love those books, so they look for hours in this images and try to find this guy here. And this is a classical template matching, right? So you know basically how this guy looks like. So you know basically what you're looking for. You know this is a guy roughly oriented in the same way always, wearing the same clothes. And let's say, okay, we have now a cutout of what we are looking for, which is our template T, and we want to find it in this scene image I. How would you do that? Okay. Do you know the term for that? Segmenting? That's windowing. Okay. When we talked about convolution, there was also this other term. So basically, it's similar to convolution what we're doing here, right? We're shifting basically this window now over the image, but having this simpler form of the convolution. Do you remember? Correlation. Yeah. So this is basically correlation what we're doing here, right? We try to correlate this template T with our scene image I, and there are many applications of such correlations or correlation algorithms. So for example, we apply the same also in stereo imaging, and we will talk about later about that, but to say it quickly at forehand, basically this is also correlation, right? So basically what we try to do here, we have our two images from our two cameras, image 1 and image 2, left and right camera. Sorry? Hey there. I'm not finished. We have image 1, image 2 from our left and right camera. And basically what we are interested in, we have a particular local location, a local window, which is our template, our image patch that we would like to identify in our image 2 on the right image. And if we have those two correspondences, right, and we will see that later, we basically are able to compute a depth for this point, basically, by having this two correspondences and by knowing basically extrinsic and intrinsic camera calibration. We will see that later how that works. But this is an important application of correlation. And now, the simplest way how you can do that is taking just the sum of squared differences here. So you take this template, shift it over the images, and yeah, we have also discussed that when we talked about the Harris corners detection. There we have also defined this sum of squared difference in this local minimal window, right? The local minimum movement of those points. We have used also the SSD values here, and this is our most easy correlation measure that we can get here. So we're just summing over the complete window, which has a size of 2K in that example. So 2K in vertical and 2K in horizontal direction. We're summing over this squared differences here to get a value for each location based on our template T. And this is the response. And basically, remember that we are interested in finding this guy in this image again, right? And now applying this problem will give you this response here. Is that a good response or not? We try to find the bright spot, right? Because this is basically the moment. This is the lowest difference. So here, basically, bright means lower differences, right? We are interested in the lowest differences here, so that here in this particular example, we would like to try to identify the highest, the maximum intensity in that image, right? And accidentally, this corresponds also to the right value here, right? But looking on this result, is that a good result for an algorithm to identify a maximum or not? Yeah, and indeed, it's quite heavy to find a good maximum here, and accidentally, it's the right one, but it will not work like that. And you said it before. So what could we do here now to make it a bit better? We could. Yeah. Are you doing that for the template or are you doing that for the image? Any other opinions? Uh-huh. Now okay. So we have now you said for the template and you said for the image. So now we have the image in a completely different range as the template. Is that doable? So if I would subtract now a zero mean normalized template from this not zero mean normalized image or other way around, what would you get then? So if you do it only for one of those two guys here, then it will not help that much, right? So you need to do it for both. And this is then bringing us to the so-called zero mean normalized cross correlation. roughly the same as here, but the only difference is that we subtract the mean and we scale it. And we scale it by the standard deviation. So we do it for the template. So we take the mean of the template, subtract it, and we divide it with standard deviation of the intensity values of the template. And we do the same for the image, right? Subtract the mean and divide it by the standard deviation in this particular window, right? This is important, right? We don't do it over the complete image. We do it only locally, always in this window of 2K for the template and for the image. And then the result looks like that. What do you think? Is it good or bad? Before we had that, now we have that. Well, it's also not ideal, but at least it's better than this one, right? Where you have a lot of those maximum responses, right? Here you at least minimize the number of maximum responses, but you have also a lot of local maximas. So you need at least to know roughly the location where you're looking at. If you need to look over the complete image, then you have a problem, right? Then you have to have a lot of luck that this is really the local maximum that you're looking at. Well, no, but this kind of thing can now be a bit extended. So this is the most basic form of applicable cross correlation that we have, and indeed this is also used in stereo vision algorithms. But in stereo vision algorithms, you can restrict the search space based on the so-called epipolar line, and we will later know what it is. But so far, I can tell you that you have to only look, given a point in the left image, you have to only search for this corresponding point in the right image along a particular line, right? And this makes the search space evenly restricted, right? So you have basically only one line where you have to look about and not searching a big region in the image. So we can improve that a bit now. And one improvement of template matching, or what better algorithm that works normally here, is the so-called distance, or applying the distance transformation and applying the chamfer matching here. So the distance transformation is provided. This distance transformation algorithm has an input a binary edge image again. So as we extracted it from the canny edge detection. And we have also a binary edge template T of a shape that we want to find, or a shape that we want to match. The problem now, if we have that here, and if we would like to, if we apply SSD and zero mean normalized cross correlation, then we would still have a lot of responses based on the matching binary images. So that brings us to a relaxed definition of this one, and this is basically the distance transformation, which is a natural way to blur the feature locations of your edge detections. Basically, the distance transformation gives you for each point in the image the distance to the closest edges, to the closest edge. So this is the formula for that, right? So the distance transform image gives you for each image locations exactly the distance to the minimum distance to the next feature value, to the next edge value, right? And I'm quickly looking for a better example here. So supposing that you have this gray value image and having this kind of canny edge detected image, then your distance transformation will look something like that, where you have basically the white, the white color represents basically higher distances to the next edge image, and the black color represents lower distances to the next image. And this basically, you can also draw that a bit simpler here. So supposing that you have your image feature from the canny edge detection, which is here the gray valued positions here. And now the distance transformation would give you for each of the locations in the image a 0 value when you are directly on an edge, right? Because there's a 0 distance. And when you are far away from the edge, you have a greater value here. You could do that with different, basically, norms, right? So the Euclidean distance, as it is applied, no, here you apply the L1 norm, which is the Manhattan distance, basically. So that means basically this particular guy would get a 2 because it has a 2 distance to the next edge image. So move 1 to the left and move 1 up, or move 1 up and 1 to the right. That's why you have here a 2. If you would apply the Euclidean distance, well, then you would have a square root of 2 here, which would correspond to the L2 norm. There are fast algorithms available to calculate that, basically. So they are running basically with O of 2 times n, where n basically is your quadratic image. So if you have a size of n square of the image, then you only need, I have to look it up again, for n grid points. So normally you would take for n grid points and m points in this in P. So the m points are your feature points. You would take n grid points, which is your image size. Basically, you would take n by m, and this corresponds to n square, since each m basically takes O of n. And that is quite a bad thing for an algorithm that you can take here. So, but there are more efficient ones available, which takes then only O of 2n. And also with the Euclidean distance, you can calculate it with O of 2n with this algorithm of Felsenswipe. So what can you do with that now? So we have our binary image B of edges and local features. We have our template T, which is also binary, which represents our template here. So we have basically our template here as a binary representation, and we have also our image as a binary representation by the edges. We take the distance transformation of this binary image, and then we do a correlation between our binary template and our distance transformed image, and we can match basically then our template by taking the correlation between the template and the distance transformed image. And why is it now better? Because we are basically smoothed out our edges, which are only at one particular point. We make it smoother and allow also a deviation of the exact location, right? So by correlating now this image instead of this image, we also get a higher response if we are quite close to the best location, right? And we get not immediately a 0 response if we are only a few pixels away of the good location, right? So this is the advantage of that. It allows for some, it's basically a smoothing of the edges, and it allows for some errors in the template locations. And indeed, this was also applied, for example, pedestrian detection 20 years ago. It's called the chamfer distance matching, and it uses basically so-called this chamfer template, a so-called binary template like that here of a pedestrian, and it tries to find this pedestrian shape in the actually image in the distance transform, right? And you're calculating basically the correlation of this binary shape within this distance transformed image, and you're taking then basically the smallest chamfer distance, the smallest correlation match here, and accept basically everything which is below a threshold, which are then pedestrians. Right. I also have that for pedestrians. So this is the result here. For a single pedestrian and for multiple pedestrian, you see basically here the matched templates. For pedestrians, you have a little bit of a problem because the shape is always changing, right? Depending on the movement of the pedestrian. If I stand like that, I'm looking from the side different if I'm standing like that, right? So you have to cope for that. So you have to visit different shapes of pedestrians. So you have, instead of only placing one template, you're placing multiple templates in the chamfer, or you're correlating with multiple templates in the chamfer image. But by that, you're able to identify, for example, pedestrians, or in a simpler fashion, as we would also be able to do it, for example, with a half transformation. We could also apply it to triangles and circles here, some easier shapes, and that was also done for traffic sign recognition 20 years ago. And this algorithm was indeed, or is still indeed, in some of your vehicles available. Whenever you have a speed limit recognition or a traffic sign recognition in the cars 10 to 20 years back, then you have an algorithm similar to that in your vehicle. And those chamfer matching algorithms can be represented or can be implemented quite efficiently, and you could also cope with multiple shapes in a hierarchical structure, right? You start with a more kind of rough representation, and then you move down in this tree to get the more fine-grained shapes, and you are able basically to identify even complex shapes like that with this chamfer matching approach. Any questions to that? Is it clear? More questions? Okay, ready for a break? 10 minutes? Then see you in 10 minutes again.